Good evening, good afternoon, good morning, everybody. We're back with another linear algebra video covering section 4.9, applications of Markov chains, with myself, Julian Fisher.
And I, Thomas Neal.
The first important definition we'll be going over to is probability vector. A probability vector is a vector with non-negative entries that add to the number 1. And Thomas is going to give us a couple of good examples of those.
So I'm thinking this is a good example.
Exactly. It's a vector where all of the entries add to 1.
And so is this one, because that equals 1.
Absolutely.
What about this one?
Not at all.
Oh my gosh, why?
Because the entries of this vector don't sum to 1. They go to 0.9, which does not equal 1.
Oh, okay. How about this one?
That one's good.
Okay, I think I got it. We can
All
move
right.
on to the next definition.
And so, the next important definition is stochastic matrix. A stochastic matrix is a square matrix where the columns are probability vectors. Thomas is going to give us a couple of good examples of those.
I think this one's a stochastic matrix.
Yes, that's a good stochastic matrix.
Okay, how about this one then? Because these are both probability vectors.
No, Thomas.
Why
Like
not?
we said in the definition, a stochastic matrix is a square matrix.
Oh, okay. So then how about that? How's that one?
That one is a good stochastic matrix.
Okay, perfect. I think I get a stochastic matrix. What's next?
Next up, we have Markov chains. A Markov chain is a sequence of probability vectors, x0, x1, x2, all together, with a stochastic matrix P such that x1 equals P times x0, x2 equals P times x1, and x3 equals P times x2, and so on for however long we want to go.
That looks like a lot. I don't think I have enough numbers to show examples on that.
Yeah, so we have a quick example with this, and so we can see that we have, zoom in. With this example, we see that we have a stochastic matrix P that's 0.5, 0.2, 0.3, 0.3, 0.8, 0.3, and 0.2, 0.0, 0.4, and then we have a probability vector 1, 0, 0. And then so whenever we multiply these two together, we get 0.5, 0.3, 0.2, which is another probability vector. And so if we take this 0.5, 0.3, 0.2 and we move it down here and multiply it by the same probability vector, we get 0.37, 0.45, 0.18. And we can continue this pattern on and on for however long we want. And every time we will be multiplying the stochastic matrix times a probability vector, and then get a probability vector as the answer, and plug it into the next equation. Let's work through an example of an application of a Markov chain. Let's say we have a city and its surrounding suburbs, and we know that every year 5% of the people move from the city to the suburb, and then 3% of the people move from the suburbs back to the city. With this information, we can assume that 97% of people are staying in the suburbs and 95% of the people are staying in the city. So this example is assuming that there's nobody coming into the city from external sources and there's nobody moving out of the cities or suburbs to go to completely different cities. So with this information, we can show it as a stochastic matrix. We can see that if you're in the city, staying in the city, 95% of people do that. If you're in the city, moving to the suburbs, 5% of people do that. If you're in the suburbs, moving to the city, 3% of people do that. And if you're in the suburbs, moving to the suburbs, 97% of people do that. And so now, if we have the initial population of 1 million people in the city, we have 600,000 people living in the city and 400,000 people living in the suburb. And we can multiply those together to start our Markov chain.
Wait, 600,000, 400,000, those don't equal 1, those equal 1 million. That's not a probability vector.
That's very good, Thomas. In fact, we can represent the initial state of our system as a probability vector, saying that 60% of people are living in the city currently, and 40% of people are living in the suburbs currently. So if we multiply our probability vector times our stochastic matrix, we get an answer of 0.582 and 0.481. This number represents that 0.582% of people are living in the city, or 582,000 people are living in the city, and 0.418% of people are living in the suburbs, or 418,000 people are living in the suburbs. And so to continue this Markov chain, we take this out of the picture and we move that back over and multiply our new probability vector times our same stochastic matrix to get our new answer of 0.565 and 0.435. And this Markov chain continue for however long we want, and each time we iterate through this, we're just going to see what the population distribution is going to be in the next year.
And from what it looks like more people are moving from the city to the suburbs.
Because we can see if we take in all of our numbers in the Markov chain right now, we see it's going 0.6 to 0.582 to 0.565 in the city, and 0.4 to 0.418 and 0.435 in the suburbs. Let's take a look at our original example of a Markov chain. We see the same work from before that we've already gone through, but let's take a look at what happens if we continue out this Markov chain to higher values. So you can hear in this excerpt from the book that it has calculated all of the values up through x sub 15. And so let's specifically take a look at what happens to the value as we move through this. We see that pretty consistently, even from x sub 3, is that the 10th digit is 3, 5, and 1. And if we continue through this, we see that that middle one is getting a little bigger, and it looks like the value is converging on a number. And you can see that especially in this last one, where it's 0.30001, 0.59998, and 0.1001. 0.10001. It looks like the values are converging on 0.3, 0.6, and 0.1. So let's take a look at a theorem. Theorem 18. Theorem 18 says if P is an n by n regular stochastic matrix, then P has a unique steady state vector Q. Further, if x sub 0 is any initial state and x sub k plus 1 equals P times x sub k for k equals 0, 1, 2, and so on, then the Markov chain x sub k converges to Q as k goes to infinity. So all that theorem is saying is that if we continue this and we go on and on and on, this Markov chain will converge on a number eventually. And there's actually a good way to work through and find the steady state vector of a Markov chain. Let's look at our original stochastic matrix of 0.5, 0.2, 0.3, 0.3, 0.8, 0.3, and 0.2, 0, 0.4. So we want to solve the equation px equals x. And then so if we move an x over, we see px minus x equals 0. Accidentally written that twice, but we're going to go with it. We know that the identity matrix times a matrix is itself. So we can say px minus the identity matrix of x also equals 0. And we can factor out a p minus the identity matrix. And we can actually solve for that p minus the identity matrix. And we end with this this matrix over here. Negative 0.5, 0.2, 0.3, 0.3, negative 0.8, 0.3, 0.2, 0, negative 0.4. So now we need to solve for p minus the identity matrix equals 0. So we want to just solve this like we would any other time. And so we take our augmented matrix with zeros and we reduce row echelon form it. And this leaves us with the matrix 1, 0, negative 3, 0, 0, 1, negative 6, 0, 0, 0, 0, 0. And so we see from this that x1 equals 3x3, x2 equals 6x3, and x3 is a free variable because it's all zeros, so x3 equals x3. Which gives us this. We have the solution to that is x3 times the vector 3, 6, 1. And then so we have that, and we want to sum all of the numbers in our solution And so in this case, it's 10, but in other cases, you might not have 10. You would have like 3 plus 6 plus 1 in this case, or whatever you have. And we want to divide all of our entries by that number, which gives us 0.3, 0.6, 0.1, which is exactly what we thought it was converging on by looking at this at higher values.
So I'm going to take over the rest of the video. We're going to take our original stochastic matrix, and if we multiply it by our steady state vector, we will always equal that same vector. This is also written as PQ equals Q. Now I know some of you are wondering, so if I want to check this, I'm going to have to solve out all the way up to x15 or higher? No, there's a little simple trick that we can use, and and it's written right here. As you know from before, x sub k plus 1 equals px sub k for a k from 0 to infinity. x2 equals px sub 1 is the same as p times px0, which equals p to the second power x equals 0, or x sub 0. So we have this new equation, x sub k equals pk x sub 0 for k to infinity. So that means we can take our original matrix, raise it to the 10th power, for example, and instead of having to do 10 matrix multiplications, you can multiply that by our original probability vector, and that will equal this probability vector here. And just to prove this is true, you can see right here, x10 equals this same probability vector. Thank you for watching. I hope you guys learned something. We'll leave you with a little question. From earlier, we had our examples with what are our probability vectors and what are the matrices, what are the proper matrix, and we have a question for the class. Would this example right here be a matrix or a vector? Think on that. Have a good one.